Hello, I'm Aurélie Chang, a PhD student supervised by Jérôme Feret and Gregor Gössler. And I will present to you our semantics of Core Erlang with handling of signals. The reason why I am coming with this semantics is that, actually we are working on fault explanation in order to debug Erlang systems. We are interested in bugs caused by non-determinism with a focus on the evaluation order of messages. And what we wanted was small step semantics, rather precise, from which we will would use to propose some abstractions fitted to our explanations. And our needs was then a small step semantics able to describe links. So here I will call them symmetrical links and monitoring links. And we needed to be able to handle signals. But our problem was you couldn't find an existing semantics which was at the same time small steps and which would cover all these mechanisms. So, we came with our own. About design choices, for us, an Erlang system is a hierarchy of concurrent processes. The interaction between these processes are only done via asynchronous signals. And we have some big simplification, which are we are not using nodes, we are not using global variables, and we are not using continuous time. And we are following some really simple rules of thumb. So our main, I'm forgetting my English. Reference is the official Erlang documentation and the initial specification for Core Erlang written by Carlson. If we need an information, but the information is absent from the documentation, we are using the implementation. And if the documentation and the implementation disagree, we use the documentation. Syntactically speaking, we are using Core Erlang over Erlang because of less syntactic sugar, and the compiler is able to propose Core Erlang from Erlang code, so it should be okay. Since an update, the receive is not exactly a receive anymore when you compile from Erlang code, so for our model, we are using a receive on our side. And as we are not modeling continuous time, the after close of a receive, we're not using the timer of the after close of a receive. A receive will wait indefinitely for a message. And we don't have a try-catch structure. So now the execution model. So in our model, a state of a system is the set of the states of the processes which are in the system. So here we are writing in full the state of the processes we are focusing on, and in the big pie we are putting all the states of the other processes. For the state of one process, you can see in red you have the identifier of the process. The second element is how we represent the execution task, which is the part about the expression evaluation. So E is the current expression. Theta is the evaluation context, so namely a map of variables and their values. Tau is a function stable, and M is the current module. And there are two elements which are dedicated to debugging info. So there is the current call stack and R, which is where we are storing the reason of the termination of a process. The third element is, 6end, which is an outbox, a lot like the outbox of the medium-step semantics of Caballero. In our model, it's a list of signals sent by the processus of identifier PID, and the list is in the order of this other emissions. We have two kinds of signals. So, well, we have signals which are messages, and the messages are treated during receive expressions, and we have all other kind of signals, and these ones are treated as soon as they are received. And well, the general form of the signal is a tuple, with the first element is a flag saying if we have a message or something else. The second one is the identifier of the target of a signal, and on the third part you have the content of a signal. And with this outbox, we should have the same guarantees on the order as described in the documentation, which are, well, if a process sends signal to another one, the reception order is the same as the sending order. But if more than one process sends signals to the same process, there is no guarantee on the order of signals coming from different processes. And well, the last element of the state of a process in our model is L, the set of links between this process and other processes of a system. And well, we have two kinds of links, monitor links and symmetrical links. Monitor links are represented, well, on the monitored process side as this tuple, saying that, well, the process is monitored by the identifier of the monitoring process and an identifier for the link. And on the monitoring side, well, kind of a mirror of this tuple, saying that, well, this process is monitoring the identifier of the monitor process and the identifier of the link. For the symmetrical link, we have just a flag saying that's a symmetrical link, so a link, and the identifier of the two processes which are linked together. For the semantics, I won't present all the behavior we modeled. And I will use a small example to illustrate the two behavior I picked. So let's say that we have a module named test, and in this module you have a function named go with 0 arguments. Well, this function just do two sums. And let's say that we have a process, which I will call parent, and its first instruction will be this thing. And well, the behavior I want to show is, well, the parent will first, with the instruction in red, create a child, a process child, which will have as first instruction a call to a function go from the module test. Then it will create a monitoring link with its child, and then it will wait for a message. About the child, well, it will start with evaluating the first sum. So, well, it's 2 plus 3. Then it will receive the monitoring signal from its parent, and it will treat this signal. So it will update its set of links, and then it will go back to the evaluation of its first instruction. So 4 plus 4, then terminates. When it terminates, it will send a signal saying to the monitoring process that it's okay, it's done, and it's down. So on the parent side, the parent will receive the down signal from the child. It will turn the down signal into a message. Then it will follow the close of its receive, because it has a message actually, and then it will terminate. So now that we have the example, let's talk about the semantics itself. So let's start with the end of the process. This behavior in our model has two rhythms. So either the process has finished the evaluation of its first expression, normally, or there was a problem which led to the end of the process. And the result in both these cases is that the process sends a down signal for each monitoring or symmetrical link, then terminates itself. And well, semantically, we used to implement that two special values. The first one is EOP for end of process, which signals that the process is about to be terminated. It still has signals to send, but it's not done yet. And the special value ended, which says that the process is dead. Furthermore, to be able to handle the signal from the end of processes, we need two types of transition. The terminal transition, with the small arrow with term on it, which we will use for the evaluation of expressions at top level, and an auxiliary transition, which will be used for the exploration and evaluation of sub-expressions recursively. Well, we have two transition systems, so we need a rule which makes the bridge between them. So it's the rule of X term. So when we are using an auxiliary transition, this means that we are making a new call, so we had to update the stack. And the only other rule of the terminal transition system is val, which is the rule that supports all the sending of signals when the process terminates. So as you can see, the process will progress to ended. It will pass the list of its list of link processes, and for each process, either monitoring it or linked to it, it will send signals saying that is down. And well, it's very theoretical. So to illustrate a bit here, what it does with our example. So I will focus on the child process for this thing. So the child process is born from the call, or from this call, which means that its first instruction will be a call to a function go from the module test. And in our model, it looks like this. So you can find here the identifier of the child process, its first instruction, the evaluation context here is empty, and we are using the normal initial function table. The current module is test. The stack is presently empty, and the reason of termination is its default value, which is bottom. Right now, the child still doesn't have sent anything, so the outbox is empty. And it doesn't have yet any kind of links, so the set of links is empty too. Well, now we can proceed to the evaluation of its first expression. So we don't have, it's an expression which is not a value, so we will have to explore a bit and use an auxiliary transition. So we are updating the stack, and we still have some calculation to do. A few operations later, we finally have the result. And well, here you can find the resulting expression. So Go did two sums, and this is the result of a second one. So 4 plus 4, 8. The termination is normal. There wasn't any kind of problem or bug, so the reason of termination is still bottom. And well, the child still doesn't have sent any kind of signal, so the outbox is still empty. And as said earlier, its has a link with the parent process, which is represented with this tuple. So it is monitored by the parent with a link of with identifier ID. Oh, sorry. Okay, now that we have a value, so now that the first expression of the child has been fully evaluated, we can terminate the process. So this is done with the rule val. So as you can see, the child process is progressing toward the ended value. Well, there is one link flag monitored by in its L set of links, which means that it will send one signal to the parent. And here is the signal. So here you can see information about the signal. So its nature, it's not a message, something else, and it's a down signal, and its destination, which is the parent. Here you have information about the link, so it's the nature of the link, it's a monitoring link, and the identifier of the link. And finally, the reason of termination, which is in this case normal. Well, now that we have sent a down signal, let's talk a bit about how we handled it. So in Erlang, well, the signals are asynchronous, and a big characteristic about handling signal is that it is automatic. A developer doesn't have anything to do to handle a signal, and it is impossible to prevent it. So about down signals, well, here is the rule who handle the down signals. So more simply, it needs two processes. So we have the processus J and the process I. The process J has received a down signal from the process I, and the process J is still monitoring the process I. And in this case, well, the signal is deleted, and the corresponding message is appended to the outbox of I. And for our example, this was ugly earlier, that's worse, but here is the thing. So you can find the two processes, PID, parent and child. You can see that the parent is monitoring the child. And here you can see that the child has sent a down signal to the parent, which means that, well, the signal is deleted and a corresponding message here has been appended to the outbox. So, as a conclusion, our contribution is, well, a small step semantics of a subset of Core Erlang. We are handling monitoring links and symmetrical links and signals. And right now, well, I am implementing it in mode. And once done, we'll go back to investigate the causal analysis of fault originating from non-deterministic message order. Thank you for attention. And well, if you have questions, feedback, or anything, I'm okay.
Do we have any questions? Yes.
With monitoring, maybe I didn't understand it. Did you consider that a monitoring link can be stacked? So if it's unmonitored, you take only one away, whereas the symmetric link is not stackable. There's only one.
I'm not sure about what do you mean?
So you can have basically multiple monitoring links between two processes.
You can have multiple monitoring. This is why we have an ID, but we can only have one symmetrical link for a pair of processes.
Exactly. Okay. Thank you.
Any more questions? I do have one. So do you know if in the Erlang OTP team, sometimes we end up discussing semantics of the language because it's not documented in the reference manual, that, as you said. Sometimes those things are not specified for compiler-specific optimizations, I think. So do you know if this work is going to be mechanized so that we have a proof that if we trust basically what you're doing in this case, then we can all agree on the same semantics?
I still don't know. I'm trying to make as many links as I can with the documentation. As you can maybe see in the paper, when I am referring to some place on the documentation, I see when, where and why I've made the choices when I make the choice. So I believe it's doable. I'm not sure I will be able to do it during my PhD, so hopefully. But,
just a comment, I think there should be some kind of formal language specification that was written by Jonas Barklund, I think. I'm not sure where to find it there, but I'm pretty sure he did some formal specification of the Erlang language.
But I know that we've ending discussing, I don't know if it was argument evaluation on functions or something, and we couldn't agree on what was the right order, so I'm guessing there are some gaps. Yeah. Or it doesn't cover the whole.
There could be some gaps in that.
Yeah.
But just like there is such document that we can make it more valuable, perhaps.
For sure. Right, any more questions? No? Okay, so